I think we'll start with a few introductions and a few comments before Professor Spanos' talk. Welcome to the CITRIS Research Exchange again. My name is Gary Baldwin. I'm Executive Director. I'd like to begin by thanking Infineon Technologies for their support of these meetings, especially for their contributions to that lovely lunch that you're enjoying. Welcome to our colleagues at UC Santa Cruz, UC Davis, and UC Merced. This meeting is being webcast, and so we hope that you are out there and enjoying whatever lunch is being served to you, if any. Many other web viewers from around the planet, so welcome to them as well. There will be no meeting like this next Wednesday, owing to the imminence of the Thanksgiving holiday the following day, so we will not have a research exchange next week. I would also like to draw your attention to the fact that CITRIS will hold its annual holiday gala out here in the lobby of the Hearst Mining Building, the Gordon and Betty Moore lobby, on Friday, December the 7th, from 4 until 7 p.m. Lots of refreshments, lots of singing, lots of merriment, and a very interesting display on a project called the Tin Cans Carousel Project, which I will not say much more about. I will just leave that to your imagination. It's actually a very fun video concept, and you'll see that as soon as it gets dark outside. We'll start that on the 7th. I would also like to point out that CITRIS is now, for those of you who only communicate through YouTube, CITRIS is now available on YouTube. All of these lectures and seminars that we hold, the research exchanges, our distinguished speaker series, are captured and stored on video on YouTube. If you go to youtube.com/CITRIS, you'll find them there. That's just been put up thanks to the efforts of Khosrow Taherian in the last week or so, and we already have several hundred hits with comments, mostly positive so far, I'm happy to say. So we'll see how that turns out. Today we're very honored to have Professor Kostas Spanos from the Department of Electrical Engineering and Computer Science and the Associate Dean for the ERSO part of the College of Engineering with us to talk about innovations at the design manufacturing interface. That's solid state design, where he's not going to talk about automobile engines or shipbuilding. It's going to be about solid state, as you'll learn when I tell you that he received his degrees in electrical engineering, starting first at the University of Athens in Greece, and then a master's and PhD from Carnegie Mellon. After 3 years at Digital Equipment Corporation, he joined the Berkeley faculty in 1988, where he has been ever since. He directed the Berkeley Microfabrication Laboratory from 1993 to 2000. In 2000, he was honored by being elected a Fellow of the IEEE for his contributions and leadership in semiconductor manufacturing. And Kostas, I think they're going to be able to tell what your research interests are from this very fine talk today. So in our normal fashion, let's welcome Professor Spanos to Research Exchange. Thank you very much.
Yes, I definitely think that some of my own interests will show through this talk. There are two things that are missing from this title. One is a clarification that this is about semiconductor or solid-state manufacturing. The other is that I'm not going to presenting the innovations here. I'm going to telling you what innovations are needed with some hints of where they might be coming from. So most talks give you the summary at the end. I would like to spare you the suspense, and I would like to give you the key message at the beginning. And the rest of my talk will try to establish why this is the case. As some of you might know, the semiconductor industry is quite famous for pushing innovation. By that we mean they keep reinventing themselves and keep changing the paradigm they do business very, very frequently. And they keep improving performance tremendously, as we all know from the consumer marketplace. Now, this has been happening for over 40 years. And now you can buy regular integrated circuits that contain more than 1 billion transistors. That's a very big number. So as this is happening, there is a transaction that needs to take place between the people who design the chips and people who make them. There has to be an agreement, so when I give you a design, this design can be realizable. Well, this transaction is the focus of this talk. And the key message here that this transaction is being strained to the point that needs to be redefined. People are facing atomic level variability. They are facing dozens of new materials that we didn't have before. And of course, we have multiple technologies that are really operating at a technological limit, as you will see. So a new paradigm is needed. And the good news is, of course, that many people are working on it, but fundamentally, UC Berkeley our team is poised to make a big contribution. I would like to brag about that at the end of the presentation. So this is the outline. A brief history on semiconductors, past and present, the design rule model, I will explain what that means, the design rule bottleneck, and the change in paradigm. So past and present, I look back to find out a point that defines the genesis of the semiconductor industry, and of course some people would argue that it was a transistor in the mid-50s, and certainly there's something to do with that. But it is the integrated circuit, the ability to put many components on one piece of one substrate that really made a difference. This is the original patent submitted by Jack Kilby back in 1964. Jack Kilby, as you probably know, he was with Texas Instruments. He received the Nobel Prize for his contribution in the year 2000. And this was the first design. And as you see here, it is a monolithic circuit. You see it on the top here, if I get the pointer. A monolithic circuit, and underneath you see the equivalent electronic circuit. This one has 2 transistors in it. A great innovation, 2 transistors and several resistors. Well, it's been more than 40 years since. Lots of things have happened. This is the, perhaps some of you have heard about Moore's law, that essentially specifies that performance will double every 18 months or so. In this particular metric, you see the transistors per die. Remember that in Kilby's patent, he had 2 transistors. So we start somewhere around here. Okay? And 5 years later, Moore from Intel looked back at these 5 green dots and say, hey, there is a law at play here. Things are really improving on a scale, so let's establish that. And remarkably, even though nobody is actually forcing or following this law, the industry followed pretty much that. And now we have cases where we have exceeded 1 billion transistors on a chip. This has been going on for more than 40 years. And chips and integrated circuits look a little bit different than they used to look back in 1964. This is a standard cell. This shows some of the complexities that you could face. You see the silicon substrate at the bottom. You see this, the transistor gates. There are many transistors on this, maybe 20 or so transistors. You see the contact holes. You see the interconnect, and some material has been removed in order to make this thing visible. And if you indulge me, a comparison between what it is and what it was is kind of instructive, and I wanted to put them on the same scale. In order to put them on the same scale, you would have to grossly magnify what Kilby did 40 years ago. And let me make the generous assumption that this wire is 1/10 of a millimeter wire. Maybe it was bigger at the time, so 100 microns. So I will still have to magnify it because this little dot here that perhaps you cannot see represents the circuit. And if I magnify it a little bit, maybe you can see it a little bit better. So you can see things has progressed tremendously. And there are some challenges with that, because the moment you decrease the size of something to this, then the real challenge begins. Remember that a real integrated circuit has 1 billion transistors, so you have to repeat this thing 100 million times. And you have to make it flawlessly and connect it without any problems. Make sure that everything works, and on the top of it, you have to sell it for a few dollars and still make enough profit to invest in order to keep pushing the technology. To say that it is not easy is an understatement, but it has been happening with great regularity. So in summary, if you go to past and present, the semiconductor industry follows different eras. In the beginning, in the 1960s, it was the novelty of the concept and the main patents and the ideas that came about. Then people have figured out a way to do it more effectively, so that was a technology revolution in the 1970s when they dropped the cost and we start having consumer goods coming out. At that time, they hit a wall because now you had an opportunity to design circuits that have hundreds of thousands of transistors. So the design techniques had to change. Design automation was necessary. So the design revolution happened in the 1980s or so, where most of these things became software products of industrial strength. Then, of course, in the 1990s, people figured out how to really improve the efficiency of manufacturing. They put controls in manufacturing, they put statistics, and they put models and diagnostics and so on. So manufacturing became very, very effective, and costs continued to drop. And now we are in the 2000s, and people are looking for the next opportunity, what is next to push. And this is what I would like to talk about. But the bottom line is that we cannot keep progressing by making things smaller anymore. Yeah, you can do this for a little bit longer, but there are fundamental limits that we are approaching, and also economical limits, as you will see. And the other thing is that the established design manufacturing handshake needs to be revised. So with that, I would like now to go a little bit deeper and tell you a little bit about this handshake, how it is today and how it has evolved over time. So I will talk a little bit about the design automation and the design flow paradigm. The design flow essentially is a term that refers to the sequence of events that need to take place from the moment you get the requirements for a complicated integrated circuit product until you actually build it. Well, on the design flow has been highly automated thanks to the EDA industry, the electronic design automation industry. It's a multi-billion-dollar industry. Most of it is in the South Bay. The emphasis of this is to highly abstract things, so people who design integrated circuits do not need to know much about the technology, because you need many more designers than people who build them. So people can push polygons, draw lines, and somebody else takes care of all the technological problems behind it. So there's a high level of abstraction. So it isolates most design from technology details. And of course, it needs to be said that the whole electronic design automation revolution owes its genesis to UC Berkeley, to seminal work that happened here in the 1970s and 80s. People like Richard Newton, of course, played a huge role, and others in this. You see the sequence here. You start with a very high level of abstraction. You describe a microprocessor or a video driver. Then you synthesize this at a fairly high level of abstraction in what is known as a register transfer logic. Then there is some prototyping. Now, don't fool yourself. This is not physical prototyping. It's still in the realm of simulation. Then there is the physical synthesis, where people start designing the shapes that are going to be printed. There is the routing, when the things are connected together. Then there is optimization. And finally, you create masks and you give them to manufacturing. And of course, in at least these last 4 steps, you have to have input from manufacturing to tell you that what is possible to do that. The form of this input is highly abstracted, and I would like to talk about that. But I would like to tell you that there are fundamentally 3 communities in this transaction. There are the people who design the integrated circuits. There are the people who develop the new technologies, the new chemistries to actually make them. And there are people who will actually have to make this in volume. So there is the design, the technology, or the process development, and the manufacturing. Design and process development interact very closely in many cases. But at some point, things have to go down to manufacturing. This was very ad hoc until late 1970s, where a book came about. It's the book Introduction to VLSI Design by Mead and Conway. Maybe you're too young to have seen it, but it's still on my desk, well worn out. And this book introduced the concept of design rules. Essentially, what it says, among other things, it explained that perhaps the way to let the designers know when it is feasible or not is to simplify it as much as possible and to give them some basic dimensions that they have to observe. If you observe these dimensions, we, the manufacturer, guarantee that the thing is going to be realizable. So all you have to worry about is make sure that electrically the thing is correct, make sure that you observe the fundamental dimensions, and it will be OK. So these are known as the Mead and Conway design rules that came about. It's to give you a flavor of how this looks like. It's a very simple concept. If you're designing, if you as an electrical designer want to connect your aluminum layer, this is a cross-section, to some kind of a substrate, you have to cut a hole into the insulator and let the aluminum flow down. Well, from the top, it looks like a hole cut on top of this resistive region. So the design rules will tell you that if you want us to make this, make sure that you observe some minimum distances. Make sure that you do not get this contact hole too close to the edge, because there might be problems. There are uncertainties in production. And make sure you don't make this contact hole too small. Right? Notice that the term lambda shows up here. The reason people use this term lambda is because design rules are meant to be scalable. So I have a set of design rules, and I'll tell you that lambda is 1 micron. You know what I mean. Tomorrow, if my process is better, then I'll tell you, you know what? It's the same design rules, but lambda now is 0.5 micron. So automatically, you can scale your design down. So everything is scaled into this lambda. Now, the design rule concept is simple, but then again, it can get pretty cumbersome. This is a fairly simple process that shows the interaction of 4 layers. I apologize I couldn't find this in color, so you will miss most of the point. But there are 4 layers that interact. There is some diffusion layer underneath. There is a polysilicon layer. There is a contact hole, and there is a metal. And these are all the people who develop the design rules try to capture all the possible contingencies here on how these layers are interact, and they generate a rule for each one of these contingencies. So notice that a simple interaction of a few layers generates a large number of rules. Now, all of them are scaled to lambda, and they can easily change. But as the technologies advance, the number of rules that you have to deal with has grown a lot. And when I'm saying has grown a lot, I mean that in a real process, you have to deal with a few thousand rules. And the rule book is as thick as a telephone book. And there are some other problems. As we move ahead, this top-down view of the design, where if you make sure that some distances are observed, you're going to be OK, this top-down view doesn't really describe the complexity. And some of this complexity now can come back and hurt the designer. This is a cross-section of a relatively modern device. The source is from Intel. It is a 65 nanometer device, or a device at a 65 nanometer node. Nodes is a term that the industry uses as they progress in scaling. They move from one node to another. And as you can see here, in this cross-section, you see these little dots. Well, these little dots happen to be silicon atoms. These little dots here happen to be silicon dioxide molecules and silicon atoms underneath. The device size is comparable to the fundamental unit of atomic size. So now you have to deal with issues that cannot be simplified so much by presenting simple dimensions. The other problem is that in the good old days, transistors were planar or flat. So a top view of a transistor like this will tell you where the source is, the gate is, and the drain is. And the channel, because all you could do is just to move things around from a two-dimensional world, didn't quite matter to you. That was an abstraction that you can live with. Transistors will not stay flat. In fact, transistors have already moved into a situation where you have clear three-dimensional structures. And in some cases, people are talking about transistors where they go underneath the top layer, and you have another layer behind it. So with all these complexities, that's another view on the complexities. The reason I put this picture here in is to make the point that a top-down view of a two-dimensional world where you can simply deal with lateral dimensions is not adequate anymore. So you can see here, this is an SRAM, static random access memory, that you have almost in any consumer electronic device. This is a closed view of the transistors, and you can see that how people use these three-dimensional structures, the spacers, in order to modulate the electrical performance. This is a FinFET, and people put different materials in order to engineer stress and strain. So design rules now are kind of losing a grasp of describing the complexity enough so that the designers can deal with it. So the problem is that rules now number in the thousands. This is not a big problem because clearly rules are not being observed manually. You don't design the layout and you look up on the book anymore. You draw the layout, and like an automated spell checker, if you draw something that is not acceptable, it's be highlighted. In many cases, it will give you a suggestion of how to fix it. So that is OK. However, when you have thousands of rules, the performance of that spell checker suffers. So now it gets in the way of doing the design. But if that was the whole problem, we would leave it alone. Unfortunately, it is not. In generating these thousands of design rules, we cannot guarantee that these rules are unique anymore. So you might have many rules that are redundant. You have a rule about this distance and a rule about this other distance, but in some context, one rule might overshadow the other. So you have this inefficiency of having redundant rules. But the biggest problem is that back in the old days, if you met the rules, your design was guaranteed. Unfortunately, that's no longer the case. So the designers are asking, why should I go through all this pain of spell checking my layout, my design, if at the end you cannot guarantee that you can build it for me? What is the point? So you are at this point now here that there is a discussion between the communities on how to deal with that. So I just want to leave you with two messages. Design rules have grown to be very cumbersome, and design rules no longer capture the complexity of the process. So meeting them does not guarantee that things are going to work. So let's talk about that a little bit and how people are dealing with that. So I would like to talk now about the design rule bottleneck, now that you know what design rules are. And the bottleneck revolves around a few issues. It's variability, or maybe I should say uncertainty, hotspots, which is an interesting term, I will define it a little bit later, and patterning, that is creating the layout, creating a pattern that is at its theoretical limit. And I will explain what that means. All right. So the semiconductor industry is famous for being fairly organized. So they maintain what is known as the semiconductor roadmap. The roadmap is a document that the industry issues together every 2 years that essentially projects the future of technology. They tell everybody this is what we intend to do in the next 5, 10, 15, 20 years. It has different scales. So the roadmap is a very thick document because it deals with all the details of the technology, and it also explains why these changes are needed. And they use a convention when they project the future. By the way, this is drawn across time. You see the years here. And there are different features here, different numbers that represent the features of technology. I will just focus your attention on one line. This is the, let's focus on this line here. This tells us that in 2005, the industry expects to be printing metal layers with a resolution of 90 nanometers, 90 billionths of a meter. And we expect that year after year, we'll be reducing that, we'll improve the resolution to 78, to 68, all the way to 32. Now, the industry is using the convention of using white when the solution is known, when we know how to do that. Yellow when, well, we have some ideas on how to do that. And red on when we have no clue how to do that. Okay? So by taking a look, you see when the next problem is going to hit you. And you can see that, well, when it comes to controlling this thing with a small variability, we are already in very shaky ground. And, well, today, that roadmap is a year ago, right? Today, we're in trouble. We don't know how to meet our goal. But anyway, this is what the industry tries to do. They try to map out everything very neatly, but there's quite a bit of a mess behind it trying to achieve it. I would like to focus on two numbers here. The objective that in 2005, the industry was printing things at 90 nanometers, and in 2013, we'll be doing things at 32 nanometers. That has a big implication. This is a kind of a caricature of a layout, a 90 nanometer layout. And the same patterns pretty much are shrunk them down to 32 nanometers, so they are smaller. Clearly, you can see why the industry wants to do that. I mean, you can fit more stuff on the same area, more functionality, more transistors, and so on. Unfortunately, if you imagine that you're drawing this with a pen, the tip of the pen has the same thickness as it's had before. The tip of the pen in this case is the wavelength of light that you use to print things. And this wavelength of light that you use to print things causes imperfections in the printing process, in the patterning process. And this circle essentially says, the circle of radius of influence says that if you change the layout anywhere within the circle, then that change is going to impact the layout in the middle. So there is an interaction now. If you put another line there, the layout in the middle is going to change a little bit because things will interact through the electromagnetic field while you're printing things down. Now, if you go to 32 nanometer, the radius of influence is the same, but now you have much more stuff in it. So you have much more stuff to worry about, many more interactions to worry about. So people use techniques known as optical proximity correction, reticle enhancement techniques, and so on. This is fairly advanced techniques using all we know about the electromagnetics of the lithographic process in order to optimize it. Really, really at the limit, but it's becoming very difficult. No matter what you do, however, it has been a while that the reality is that what you print is really not what you get. This is a layout as drawn. In fact, you see two layouts here. These are metal lines that are supposed to be connecting things on an integrated circuit. To give an element of scale, the width of this might be 1/10 of a micrometer, say. So this is the layout as the designer intended it. Then some kind of automated software took this layout and changed it a little bit, made little changes in order to compensate for imperfections in the printing process. And then finally, you get to one fine day, you print it, and you see how it looks like. And this is a good result. Okay? The reason this is a good result is because nothing sorted out. All the contact holes that were square, by the way, now they are round. You cannot resolve the corners. All the contact holes are in the right place, so this thing would electrically work. Now, there is such a difference between the simplistic view of the designer and the reality of making this thing that is giving us all the headaches. So, now, even though electrically this thing would work, its performance might be very different than the designer intended. The values of these resistors might be very different. It will vary from one time we print it to another, and so on. So you got lots of variability. And variability comes in many flavors. This is a real picture that shows polysilicon lines drawn next to each other. I put it there because I want you to notice that these lines are not smooth anymore. There is a roughness on the side. The roughness is because of the molecular structure of the photoresist material that we use in the patterning. So these big molecules leave fundamentally an imprint on the line underneath it. So you have to deal with that. That's a level of variability. This is a picture of dimensions measured and plotted on a plot across a wafer, across a disk of silicon. And you can see on the scale here, on the color scale, we saw the size. All the sizes were meant to be the same, but they are very variable, as you can see. Then there is the issue of proximity that surprises most people. This line is drawn exactly the same as this line. The only difference is that you have some patterns next to it here, while you do not have these patterns next to it. Well, you know what? The presence of a pattern in proximity to that makes a change, makes a fundamental change, and makes things differently. And finally, when you deal with all this, you still have to remember that in a factory, you're going to have day-to-day variability. Your machines are not going to operate the same way. The focus of your exposure tool is going to drift, and so on. So you have now variability on very many different levels to deal with. That's actually a very interesting result done by some folks in ECS, led by Professor Nikolic. This is an example where they made a chip. The whole purpose of the chip is to measure process variability. So they have a circuit here, repeated thousands of times in an array, and then they measure them to see how they spread out in performance. And they played different games with the layout. The interesting thing here is to see the distribution of performance. Now, the different colors that show up in grayscale correspond to different chips because they made different chips. Each chip had its own distribution. So there is the dark one here, the next to it, and so on. So there is a spread chip to chip. Then there is a spread within the chip. Here. You can see that. But most interestingly, this spread depends a lot on whether there is another pattern next to the pattern that you're making. So what I'm telling you is that I'm building a circuit, and I make it run, and I measure its performance. And then I lay another wire next to it. This wire doesn't touch my circuit, has nothing to do with it. But its presence alone, because things are at the atomic level, will change the performance of my circuit. If something is next to it, okay? Because next, in this case, is a few billionths of a meter, right? So even though it might not be electrically connected, it makes a difference. So people are discovering that things are not so easy anymore. But they might have been hard in the past, but as the technology gets smaller and smaller, you lose yield. You lose a percentage of devices that you could have sold for money. You lose them because you have all these types of variability. Some of it is random. Some of it is systematic, but it's patterning related. Some of it is systematic, but it's related to the performance of your circuit, and so on. So people must do something about that. And finally, another example that explains a little bit more directly why design rules not work anymore. The layout that you see on the left, just look at the straight lines for now, not the curved lines. The layout that you see on the left met all the design rules. No design rules objected to it. But when people did a simulation to it, simulated to see how the real layout will look like, and these are the green kind of rough lines that you see next to it here. Notice that this end of this line is not square anymore, and this corner here is kind of rounded like this. Well, they figure out that in this particular instance, things get too close. So here's a case that you meet the design rules, but when you simulate its performance, it will tell you that this thing is not going to be manufacturable. This is known as a hotspot. Hotspot meaning that you go through my layout and find all these cases through simulation, and I mark them down as spots that are going to give me problems. And then I have to do something about it, and people are working on many techniques to find hotspots, and then many heuristics to not only find them, because you might find 1 million of them in a layout, to automatically clean them or reduce their temperature, as they say. And in this case, they do it by modifying the layout locally. That's something that the designer doesn't want to do because it's so tedious, right? You have to do it 1,000,000 times on the layout. All right, and a final challenge. There are many. I'm just picking on a few. When you print things in photolithography, there is a fundamental limit. If your optics are absolutely perfect, no distortion whatsoever, your light source is absolutely perfect, your photoresist has excellent, perfect performance, there is a fundamental limit. And the fundamental limit, known as the Rayleigh limit, tells you that to print something small, this is the size of the feature that you want to print, this is going to be proportional to the wavelength that you're using, lambda, divided by the numerical aperture, multiplied by a factor known as the K1, or the difficulty factor. Okay? Now, lambda, in our case, is about 200 nanometers, 200 billionths of a meter. It's way below what is visible, but that's what the industry is using, 193 nanometers to be precise. The numerical aperture, I don't know how many of you are in photography, cannot be more than 1. Okay? In fact, can approach 1 with great difficulty, but cannot be more than 1 unless you play some really tricky games. Okay? So, and K1, for reasons that go beyond this presentation, cannot be smaller than 0.25. There's a theoretical limit there. You simply cannot print when K1 is below 0.25. So people put all these things together and say, okay, here we are. This is the table. We would like to print 100 nanometers, 65 nanometers, 45, 32, 22, 16, and 11. These are the years that we intend to do that. Okay? And let's see what technology you have available. If lambda is 248 nanometers, well, maybe you can do the 100 nanometers, but beyond that, you cannot do it. So then we have to move to a different laser source and go to 193 nanometers. Then you can play with numerical aperture. The biggest that we can do it is in the 0.9 something or so. But if we take the whole thing and immerse it in water, we play a trick with refractive indices, then we can game the system into thinking that the numerical aperture is bigger. So now you have a very complex photolithographic system that is immersed in water, and you can have a numerical aperture of 1.2, 1.35. To go to 155, you have to immerse it into something even more exotic than water. So it becomes very complex. And then we have to go and play what is known as extreme ultraviolet lithography, where essentially you play with X-rays. People don't want to do that yet. That's super expensive. As in, each system that will do this costs $50 million. So they are not ready to go there yet. Anyway, so 193 nanometers at the workhorse, and you can see here the K1 factor, and you can see that it is getting very close to the theoretical limit, and oops, at 32 nanometers it hits it. Means that you cannot do it. So you have an option. You can go to this exotic X-ray kind of source, or play another trick. And the trick that people play is they say, wait a minute, maybe I can take my layout and split it into 2 components. I can print easily these, because the pitch is very wide. I can print easily that, and if I print them on top of each other, then wait a minute, I have managed to cheat and double my pitch and double my density. This is known as a double patterning. It sounds difficult, and in reality, it's much, much more difficult than it sounds. It is almost impossible to align. You have to be, as designers, you have to deal with where the layout is going to be cut off because it might be electrical implications. And then, of course, in the end, you have to measure the whole thing to make sure that it came correctly. But that's another problem that design rules absolutely do not capture. And the double patterning is going to happen in the next generation, maybe a year or so from now. All right, so at this point, people might say that maybe you should throw in the towel. We're done. There's not much more you can do. This is a view from manufacturing that actually brings more bad news. This is years, 70s, 80s, 90s, 2000, and 2010. As you know, the semiconductor revolution is also known as the silicon revolution because silicon is the fundamental element that is being used. And for many years, it was silicon plus maybe half a dozen other elements that were used. So boron, arsenic, silicon, of course, and phosphorus, oxygen, for whatever, and some metals, aluminum, and now copper. So very, very few elements. But as we try to make things faster and smaller, we find it necessary to keep introducing new elements. And now, essentially, cover a good chunk of the periodic table. So it's not silicon anymore. Yeah, silicon is a big thing, but it's many, many other things that you have to worry about, each one of them bringing problems with repeatability, cleanliness, and so on. The problem with lithography is that the wavelength of light has been reduced, but the things that we try to print reduce even faster than that. So now we're still stuck at 193 nanometers, but we're printing 45 nanometer things. So you have to do double patterning, we have to do immersion lithography, we have to do aggressive optical proximity correction. A big mess. I mean, there is an industry that thrives down here providing these solutions, by the way. And then, of course, as you know, semiconductors have been built in clean rooms because, well, you need them to be clean. If you have any defects on them, these defects, compared to the size of the things that you're doing, is huge. It's going to damage what you do. Our ability to keep things clean has bottomed out. It has bottomed out because back in the good old days, we only had to care about defects that are in the size of about a micron, huge defects. But now that you're down in the 45 nanometer, you have to worry about defects that are much, much smaller. And guess what? These are very difficult to regulate. So as you can see, at about 1995, we started living with environments that are now inherently dirty, because at that level, we cannot clean them anymore. Okay? Now, if you happen to be in the metrology business, if you happen to be making equipment to measure things like KLA Tencoris, and if you happen to have a near monopoly on that, then you will be extremely happy because look at this. Back then, they only had to measure a few things in the lab so they could sell a few tools. But now, they're really going to be doing very well because there are so many more things that need to be controlled. Final picture. Is it time to end the revolution? This picture might suggest that. There are lots of pressures in here, and I would like to focus on the financial pressures. The increasing R&D costs for 180 nanometers, you can develop a new technology with a few $1 million. For 45 nanometers, you need $500 million to do it. If you wanted to build a new fab, a few $1 million would do it back then. Now you need multiple billions of dollars. And by the way, the consumers are expecting new products very, very frequently. For example, if you're making DVD players, the life cycle of the product is less than a year these days. So they expect innovation, right? So you have to keep coming up with new products. So is it time to stop the revolution? The answer is no. There are ways to move forward. And I'll give you some examples of how to do that as I close my talk. Process variability might be a huge problem, but it can be modeled and it can be codified. This is an example where you see the variability of some dimension across the wafer, and this can be broken down to the different levels of abstraction. So you can break it down to variability across the mask, across the field, the photolithographic field, across the wafer, due to the photolithography equipment, and some random component. So variability has both random and deterministic components. All you need to know is to measure them and codify them in a way that you can put them in automated tools. This is a simple example of how this can be done. This is a test chip where we measure different devices. Just going to focus on that. And you can see that the variability in these devices really depends on the layout context around it. So you have lines that are close together, lines that are further apart, lines that are further apart. And you can see that the values on these lines really depend on that closeness, something that we knew. So if you were to describe it, you have to build models that describe the variability of the layout as a function of what is around it. Okay? That is now well established. The variability model is hierarchical. You have to have components to tell you what is happening across the wafer. This is a one-dimensional view of a wafer. I just didn't want to complicate it too much. So this is the center. This is the edge of the wafer. And from wafer to wafer, you might have a standard deterministic pattern. And as you go from one wafer to the other, this pattern might change. Random variability wafer to wafer. From one exposure field to the next, you might have some variability. And others as well, including the pattern-dependent variability. What can you do with it? If you have this information, and by the way, we do have it in some toys processes here at Berkeley, you can do what is known as statistical design. Statistical design is not a very complicated project, a very complicated process. What you do is that if you ask me to make a circuit, I can optimize its performance as a designer. But I will optimize its performance thinking that this circuit is going to be produced as a big statistical distribution. So I will optimizing the moments of that distribution. Okay? That involves circuit sizing, which I will not go into it, and layout optimization. I just want to go to these few equations that I have in this presentation. That says that this can be done fairly simply. For all its complexity, an integrated circuit is nothing more than a sequence of switches and capacitors. Switches, resistors, and capacitors. Yeah, there is much more to that, right? But you can simplify to the point that you turn a transistor on, and when you turn it on, it sends a signal, and the signal has to go through a resistor and charge a capacitor. And then from that point on, it has to go to another one of these stages, and another one, and another one, in what is known as a critical path to send a signal in a large distance across a circuit. So in this critical path, you can perhaps optimize its performance by changing the length and the width of the transistors. And you do it in a way that what you optimize is the statistical distribution of the performance rather than the fixed value of the performance. So it's a simple model, this example. Simple models can be cast into a nonlinear optimization problem with a manageable number, with surprisingly a manageable number of parameters for all the sizes that you're talking about. Just go to the punchline, and the results can be quite encouraging. These are simulated results, simulating the variability of the process. This assumes that I build a large number of simple products, and this is on the blue. It's the performance of the product that was optimized without understanding the variability of the process. So it was the so-called deterministic design. And on the one here is the one that actually took advantage of the variability of the process, the so-called statistical design or the generalized variability model. Now, we make things to be fast, so speed was at issue here. We want to make things that are fast while they observe some other performance constraints. And you can see here statistically, even though you might find a few examples where the optimized product will give you things that are slower than the deterministic product, statistically, the optimized product does much, much better. Okay? All right. So go back to the design flow as I conclude my talk. That is really an opportunity to change that design flow. So you have the synthesis, the prototyping, the routing, the optimization, and the sign-off. And at some point, you have to take into account what is happening in manufacturing, not just by taking design rules, but by being able to simulate what is going to happen and optimize against that simulation. And this simulation has to be statistical in nature, a Monte Carlo kind of simulation. That means that this model has to be very fast because you have to run them many, many times, and this is part of the challenge. That's what we're trying to do, and actually quite a bit of the industry is moving in that direction. And it is these feedback loops that you see here that makes our life difficult. Because you have to design something that is very complex, 1 billion transistors. You have to simulate it, that takes a lot of time. And then you have to go around and do it many, many times while you're tweaking things here and there. And this is the big research problem that we'll try to address. Faster, accurate simulation. Design rules are changing as well. People are used to have just a design rule set that no longer guarantees yield. Well, guess what? Now people say, OK, we'll give you 2 sets. They're the design rules that you have to follow. If you don't, all hell is going to break loose. But here it is some recommended rules. You are highly encouraged to follow those as well, because this will guarantee the missing yield that the basic rules cannot guarantee. Why have 2 sets? Because the recommended rules are much more complex in nature. And you don't want to mess with them unless you have a high-end product in mind that you really have to hit a high performance. So the paradigm is changing. It's getting more complex. Manufacturing now talks back. And yes, IC designers are working on what so-called robust designs, or designs that are immune to variability. Process development people care a lot about controllability that they didn't used to. And there's quite a bit of novel metrology and manufacturing for design techniques, MFD, happening on the production line. But the biggest thing is that manufacturing now has to communicate many, many more things than they used to. Flexible design rules, variability models, first principle manufacturability models, hotspot libraries, and so on. So, is it over? This is the slide that I saw before. As you can see here, the trend doesn't seem to be flattening out. So, yeah, it's been a year ago, but I don't think that you will see any flattening out yet. The basic thing is that the way that we achieve innovation is going to be different. And this is a hopeful view. When it comes to the future, you go back to the roadmap and you find out what the industry thinks is going to happen in the next 20 years. And industry thinks that the architecture of integrated circuits is going to change fundamentally. So this is an integrated circuit, but it's going to have multiple processors and many data processing engines like video drivers and whatever. Many. So you have this modular architecture. And if you have to wonder whether the industry believes that you can move forward, take a look at this graph. This is the graph that tells us about the processing speed that they expect to deliver to the consumer year after year. And the processing speed is shown here in teraflops. And it's, I want to point your attention to the fact that this is a logarithmic scale on the right. And today we have about a quarter of teraflop on a very high-end consumer product, desktop product. They expect this to go to be 300 times bigger, okay, in about 13 years. So 73 teraflops. But the interesting thing is how they expect to do it. They expect to do it by capitalizing on this architecture where you're going to have now multiple processors and many more of these modules here. And this, by the way, present a way to beat Moore's law, the way to keep the Moore's law going. There is no good reason to keep all these processors on the same stack of silicon anymore. They're hybrid techniques, so you can build smaller things and bring them together at the end, even though there are huge challenges in doing that as well. But that's another way things might go. Finally, I would like to close by bragging a little bit about the overall work that we were doing and planning on doing at Berkeley and the University of California in general, actually. Our target is facilitating all these things at 32 and 22 nanometer nodes, where technologies are going to be already quite exotic in both in lithography and in the required computation and modeling. So you see the tools that are going to be necessary. We do this by assembling a good team of faculty under our capable leader, which is Kamis Frappula, Professor Pula, who I do not see here today, even though I promised him free lunch. But anyway, Professor Pula pulled this team together. I'm proud to be one of them. I would like you to notice that this is a very multidisciplinary team. These are people who do fundamental modeling down at the equipment level, people who do design flow at a very high level, people who develop new devices, people who understand lithography, people who understand planarization, and so on. And it is necessary because the problem is indeed multidisciplinary. And I would like you to notice that these people come from not only from UC Berkeley, but also from UCLA and UC San Diego, and many different departments. The problems that we try to solve, first thing is you don't always get what you want. What Kamis meant to say by that is that you print something that looks neat on a layout and it looks absolutely different when you print it. How do you solve this problem? By modeling the heck out of it. So there's going to be quite a bit of effort on that. The radius of influence that I mentioned before, now things interact heavily. Again, now the solution to the problem is to make sure that the designers have in place the tools that deal with this interaction in real time and do it very efficiently. Time isn't on your side. That means that yes, you can do all these things. It will take years to run these simulations. So computational efficiency is one of the goals in our team. And this is the structure that we put together. So you have people working on the fundamental studies to understand how the technology is moving, next generation lithography, next generation planarization, and so on. Make sure that we can model these techniques effectively. And we deliver what is known as DFM tools. These are designed for manufacturing tools that are being used by the designers. And MFD tools, that's the mirror image of that. That's manufacturing for design. Even though my focus goes on the design side today, people in manufacturing need to know more and more about what the designer intended to do. So they're not just saying something and blindly print it. They need to understand what they're trying to do. So there are many tools that they need to capture that as well. Now, to do this, you cannot do it in a vacuum. You have to bring together a team that does it every day, and the team has to come from industry. So we assembled a team of companies that is going to be co-funding our project and is going to be mentoring this project. We have, of course, the big vertically integrated companies, the companies that do design and manufacturing and process development. We brought in companies that do heavy-duty design and have somebody else build it, like Marvell and SanDisk. These are the people that actually suffer quite a bit from this interface because they do not control manufacturing. They have to send things to Taiwan and to China. And they expect that what they build is going to be manufactured, what they design is going to be manufacturable. We have to bring in foundries. By the way, this is a program to be funded by the state of California, so we're limited to companies that have bases in California. Or else you would have seen TSMC and CITRIS and many other companies here that have a very big interest in joining. And of course, you have to bring the design automation industry, the people who do all this big industrial scale design automation software. And you have to bring in the suppliers, people who make the lithographic machines, the etchers, the metrology tools, the chemicals, the masks, and so on. So you have an ecosystem that I think is quite complete and quite diverse that will be working with them in the next 4 years. Just to repeat the key message, innovation is great. It's going to keep on going on, I think, but its mode is going to change. And primarily the interactions between design and manufacturing are going to change. And I think that we're in a very good position to play a key role in that. Thank you.
Thanks, Costas, for a great talk. We have time for some questions. If anyone has any, raise your hands high. I know it was completely clear to me, so aha.
Costas, you focused on manufacturing, I guess, your area. But there is currently also another sort of dimension to this puzzle, right? There are lots of people looking at totally different devices that, for various reasons, right? What do you see? How do you think that that was going to play into the evolution of semiconductor technology?
That's actually an excellent question. People are talking, Professor Hu coined the term of post-silicon electronics, right, where not only you have different devices, but you have so many other materials, and you try to bring them together on different substrates. I don't think this is going to change the paradigm or the main thrust of what we are worrying about. At some fundamental level, people have to design against these new devices. And at some fundamental level, there has to be a contract between people who design and people who build. And new devices are not going to make the problem simpler. I think they're going to make it more complex. So techniques of capturing that manufacturing complexity have to be strengthened there as well. Yes?
Okay, another question back here.
So we hear a lot about yield. I wonder what the optimum yield is. If it's too low, you don't make money. If it's too high, you're not really stressing yourself.
That's actually an excellent question. What is the acceptable yield? That depends a lot on where you are on the marketplace. If you are Intel and you're making the next microprocessor, and for a few months you're the only one that has it, you can sell it at a premium and you can survive with a very low yield. However, if you're making memories and your yield is not 99.99%, you're dead, because the margins there are almost zero. So it depends a lot. Now, that differentiation was very prominent in the past. Today, even if you are Intel or AMD and you have the new hot microprocessor, you're not going to keep your lead for long unless you have high yield and you are able to scale up and drop the prices very quickly. So to answer your question, for microprocessors today, it has to be in the 80s or 90s, to be acceptable in the beginning in order to make any money. And for memories, it has to be nearly 100%. Now, how do memories achieve yield of 100%? Well, they use redundancies. They make their chips tolerant to yield failures. So if a portion of the memory fails, you can still sell the memory for a smaller denomination, right, and so on. So people play tricks like that. But for the past 20 years, the industry has been used on the edict that the yield has to be almost 100%. And now they're being squeezed down. And they say that the next 10% of yield is just too expensive to achieve. So we're going to live with 90%. Yes.
Do you have any final questions? Okay, well, let's give him a nice round of applause. Thank you, Costas. And just, again, there is no research exchange here next week. We'll be back on the 28th, so have a great Thanksgiving.